Time, let us start. Um, but before I introduce the speaker of today, let me just tell a little bit about the housekeepings of the class. So basically, this is the last lecture that we have for the extra credit, and I have not posted the extra credit points in the Canvas yet, but hopefully, maybe today or tomorrow you will get the extra credit. This is almost the last week of the semester, and thank you for all of you for coming for the lecture. And you will see your grades by next week or so. And if you have some trouble understanding them, or you have some things to clarify, let me know. By the last day, I think it is around 10th of December, last day of the class, so that we can sort of resolve some of the discrepancies. So that housekeeping out of the way, let me introduce the speaker of today, Dr. Ravi Sinha. It is a great pleasure to welcome you for this series of lectures. This is the last in the series of lectures that we have. Actually, this kind of a topic I wanted in the beginning of the class, so that, as you know, this is a general education class where students, upper division and lower division general education class, where students from non-science background take this class because they like astronomy and want to broaden their science content, so that they become more wise in their later life. So that is the purpose of this these classes. So in the beginning, if we have this kind of a lecture, it will be really set the tone why you should be science educated, or and the best thing is why you should study astronomy. So that is what I had, but the idea came in the middle of the semester, so to my mind, and then I thought, okay, we will anyway start this, and then maybe later classes, later years, I will include this. And when I tell people that we are doing this kind of a thing during pandemic, where most classes are going online, it is really appreciative. So so this kind of this topic, like why you should study astronomy or science, even though you may not go for a science career. So this lecture kind of sets that tone. And let me, when I thought of this topic, I thought of Dr. Ravi Sinha, to whom I knew when I was a graduate student in India. And he was fresh from MIT, and he came as a bright and enthusiastic young man at the time. Of course, that is quite a bit, almost 30 years back. But we were all motivated by his presentations, lectures, lifestyle, and everything. Many of our generation were motivated by him. And I still remember, because I can give his bio, means he did this, he did that, and so many other things. But my introductions are basically how did I know them and why I am motivated by these speakers. And in that context, I still remember till today one of the lectures that he gave when he came to our institute where I was doing my PhD. And that is on the electromagnetic theory, how the Maxwell equations in electromagnetic theory, you have Maxwell equations which are profound, which are the basic of most physics, and how they can be derived from theoretical concepts without any experimental results. Even just you make some basic theoretical assumptions, and you can derive all of them. And I was just young at the time, and I could understand what he's talking, and it was profound. So I always, whenever I talk to people about my understanding of the classical theory of electromagnetism, I quote this. And so over the years, he has been engaged in doing a lot of social work. And so he understands very well the foundations of science, modern science, and its relevance to the society. So I thought this is appropriate. We have an appropriate speaker for this kind of a topic. And so then the first thing came to my mind was maybe I should contact him. And then when I contacted him, he agreed kindly. And even though right now he's speaking to us from India, and even though in India it is quite late now, almost 10:30 in the evening, late in the evening. And so we are really grateful to him that he's speaking to us today. And he has been doing a lot of other work, and you can see them in internet, and I don't want to take a lot of time in describing those things. But this is what motivated me inviting Dr. Ravi Sinha to give this lecture. So we are really glad that he agreed, and he's today this thing is happening. And so with this, I would invite Dr. Sinha to give this lecture. Dr. Sinha.
Thank you, Devi, for the kind words. And thank you all in advance for listening to me. And please bear with my accent, you know. I could never drop it, even though I lived in your country for a number of years. Most of this evening or this morning, depending on where you are, I will be basically talking about how cosmology has become hard science supported by observational data, and that has happened mostly in last 20 or 30 years. I'd like to make an argument for you that cosmology is going to be the science of the decades to come. So we will come to that. Mostly I will talk about cosmology turning from stories and mythologies to hard science in last century, in last 30 years. And I thought, let me see if I can share the, just 1 second, share screen, yeah. I hope you get that. Oh. Okay. So, yeah, I thought that you can get a good picture of how it has happened in recent decades that cosmology has become an important part of physics, observational science, by looking at the Nobel Prizes given in recent years. In 21st century, for example, by now 20 Nobel Prizes have been given in physics. And out of those 20, 6 of them already have been given to people who have made contributions to astrophysics, cosmology, or astronomy, and so on. Including this year, you would remember that it was given, it has been awarded to Roger Penrose and also to 2 people who discovered the supermassive black hole at the center of our galaxy. The important ones have been this century, 2017, to Rainer Weiss, Kip Thorne, and Barry Barish of for the discovery of gravitational waves at LIGO. And in 2011, you know, some of you may know that Perlmutter, Schmidt, and Rees were awarded Nobel Prize for their 1998 discovery that the expansion of universe has been accelerating since last 5 billion years. So you see, out of 20, already 6 to cosmology and astrophysics related physics. And if you compare that with 20th century, the 100 Nobel Prizes of 20th century, at best 5 you could count that were related to cosmology and astrophysics. So that should give you a picture how cosmology and astrophysics and astronomy has become an important part of observation and data supported hard science. We will get into this thing later. That will be bulk of the talk tonight or this morning. But let me begin with this mythologies about cosmology. Now, all cultures that you know about or you investigate, you find that always there are some creation myths, how the world came about, how human being came about. Most ancient raise a question rather see that the cultures which had most interest or questions or supposed answers or mythologies about origin of universe, why did those cultures did not make that important contributions to cosmology as science as modern science that was born in Europe in 16th, 17th century. That culture and that modern science ended up making those contributions. I will not answer this question, but I thought that I will put in this question because I will make some observations about modern science in general towards the end. The first example I took, I am from India, so I took from my own culture, and Rig Veda is the oldest scripture that we have, probably composed 3,500 years ago, 1500 to 1200 BC. That is what modern scholars, date Rig Veda's time of composition. And this hymn of creation, this Nasadiya Soot, as it is called, is there, which is 7 hymns. I have just quoted the translation of 3 of them here, first and third and sixth. And if you read them, you see how 3,500 years ago, Indian poets and thinkers, or whatever you call them, philosophers, they were initially wondering about beginnings of the cosmos. The first one you see says that then even non-existence was not there, nor existence. There was no air then, nor the space beyond it. What covered it? Where was it? In whose keeping? Was there then cosmic fluid in depths unfathomed? And look at the third one that tries to answer it. At first, there was only darkness wrapped in darkness. All this was only unillumined cosmic water. That one with capital O, that one which came to be, enclosed in nothing, arose at last, born of the power of knowledge. So, okay, kind of answer you would probably expect, from some ancient poet or thinker. But what is special about this one is the kind of skepticism and the kind of thoughtfulness and the kind of curiosity that is there, which is unusual for most religions and most cultures. Look at the 6th sukta or 6th hymn. It says, but after all, who knows and who can say whence it all came and how creation happened? The gods themselves are later creation. So who knows truly whence it has arisen? So this is in the Indian culture, 3,500 years ago, these hymns. Then later, 6th or 5th century before Christ, in the in the Hebrew Bible or in the Old Testament, Genesis 1.1, everyone, gets to hear about it or read it sometime or the other. When in the beginning God created the heaven and the earth contained, shapeless, God said, let there be light. So this is not as abstract, not as a skeptical, this is more definitive, but you can say that this is also more direct or more it's if you don't mind, I will call it less philosophical than the older one. And the third one is not really a myth. Third one I chose, Aristarchus of Samos, the Greek philosopher, who long before Copernicus, in the third century before Christ, he proposed heliocentrism, that sun is at the center and earth goes around it, or planets go around it. And not only that, he very ingeniously devised a method to measure the distance of sun from earth. The actual measurement was off because, in those days, supporting data, there were some mistakes in the supporting data, but the method was impeccable, and he could estimate, he estimated the distance of sun to be 20 times the distance of moon. Actually, it is 400 times the distance of moon. But the accuracy is not the point. The point is that he devised a method to measure the distance of sun. I chose these three examples to keep in mind. I will come back to it towards the end, and ask the question that out of these three, and if I had time and if that was the main topic of the talk, then I would have quoted more from, say Egypt or China or Arab Islamic, cosmology and so on, because all religions have their own cosmologies. All ancient civilizations have their own cosmologies. But I just chose these three examples to contrast that today's cosmology is not the creation of Indians, and that today's cosmology is not the creation of Christianity, even though you can say that most of the debates that eventually gave rise to modern science arose in controversies and debates within Christianity. And Greece, that is most surprising, that which was scientifically and philosophically most advanced, civilization before the Christian era. When modern science came about, they were, where in Europe modern science, Greeks were not an important contributor to that, So you see the ancient civilizations which had most interesting creation myths and which were most curious about how the cosmos came about, they got left behind, and we have to, and there is no one answer to that, but we have to keep that question in mind. With that, let me move to the modern science part, the scientific revolution of 16th and 17th century. Mostly it consisted in overthrowing the Aristotelian dogma, the earth-centric cosmos, the earth is at the center. Aristotle saying that earth is at the center of the universe, and everything tends to fall towards the center of the universe. So everything tends to fall towards center of earth, and so on. Copernican revolution happened in 16th century with Nicholas Copernicus publishing his book in the last year of his life, because he was afraid the church will punish him for going against the Aristotelian or the church dogma. So he had constructed his theory based on some observations and some thinking of that the sun was at the center, and the observations or the data could be explained much better by taking sun to be the center and earth and other planets going around it. But he kept quiet most of his life, in fear of the church. And in the last year of his life, he published the book. The scientific revolution, which is often known also as the Copernican revolution, was not just that, not just the question of heliocentrism. The scientific method, came about. It was a long history. It took 200 years for the scientific revolution to mature or to complete. But Francis Bacon, for example, in an early 17th century, late 16th, early 17th century, played important role in proposing modern scientific method. Johannes Kepler, many of you would know that he was the one who, based on observations of Tycho Brahe, he came up with the elliptical orbits of planetary motion. All planets going around the sun move in elliptical orbits. That came about from Johannes Kepler's three laws. I don't have time to go into all technical details, but elliptical orbits, remember that. And then, of course, the great Galileo Galilei, who first proposed the inertial motion. What is known as Newton's first law of motion is basically a contribution of Galileo Galilei, that it doesn't make a difference if you are sitting in your room, or if you are moving in a train or in a rocket at constant speed in a fixed direction, which means with constant velocity. The laws of nature would be same if you measure in your room or in your rocket, which is moving without acceleration. So that is the first law of motion of Newton. But it was Galileo who first propounded it. Of course, he is known for inventing telescopes and discovering Jupiter's moons and so on. And finally, Isaac Newton, 1642 to 1727, he was the one who put together the first complete system of modern science. He propounded the laws of motion, he propounded the law of gravitation, and in 1687, he published his magnum opus, Principia Mathematica, and that, you can say, was the culmination of the modern scientific revolution. We are talking of cosmology, so in a way you can extract Newtonian cosmology out of whatever Newton wrote and talked about, and the key parts of Newtonian cosmology is that space is absolute, infinite, and fixed, and it is unaffected by matter and motion. So space is absolute. Nothing can be done to it. You can move inside it, but your moving inside it does not have any influence on space itself. Same way, absolute time, which always flows at fixed rate, completely unconnected and uninfluenced by any body or any motion, any matter or any motion. And the cosmic picture, what the cosmos is like, Newton would say that space is infinite, universe is static, and it is infinitely old, and all the stars are uniformly distributed in this infinite space with more or less the same luminosity. Luminosity means whatever energy the star releases per unit of time. So roughly with the same luminosity. But Newtonian cosmology, of course, is not sustainable, is because it has grave theoretical problems. Again, I just wanted to mention it to you, give you a flavor. I cannot go into all the examples of the problems that Newtonian cosmology had, except that I will mention one, which is known as Olber's paradox. If Newton's cosmology is how the cosmos was to be, then there will be no night sky. There will be no night sky means there will be no dark sky ever. The whole sky will be uniformly illuminated more than a sun, as if it is surrounded by a sun. And you can easily imagine why that would happen. That if the cosmos is infinite, and if the stars are uniformly distributed in that cosmos, every spherical shell that you will imagine will have stars, and that spherical shell will have some luminosity, and these spherical shells containing stars are infinite in number, from the nearer ones all the way up to infinity. And those of you who know calculus and so on, you can easily see that the luminosity, the total luminosity, total intensity of light coming to you from entire sky will be infinite. As physicists say, it will diverge. That is known as Olber's paradox. Of course, a sky is nothing like that. So and if Newton's cosmology was true, that is how sky should look like. Of course, if Newton's cosmology was true, and if sky was such that it was surrounded by a sun all the time, there will be no life on Earth, among other things. So obviously, it is not true. Scientific cosmology really begins with Einstein. And many of you may know the story of Einstein. He is the one single figure who gave rise to most of 20th century physics, or at least the theoretical foundation of it. This patent clerk who had great difficulty finding a job, when he found a job as a clerk in patent office in 1905, he wrote 5 papers, and as people often say, each one of those papers would win somebody a Nobel Prize. But while talking of cosmology, we will talk only of the theory of relativity. In 1905, he came up with special theory of relativity because he was trying to reconcile Newton's laws and Maxwell's laws, and there is a fundamental contradiction between them. And in order to reconcile Newton's laws of motion and Maxwell's electrodynamics, he had to come up with special theory of relativity. Special theory of relativity is nothing but Galilean relativity. You remember, Galileo said that as far as inertial frames, people moving with constant velocity with respect to each other, they will measure all natural laws the same. The natural laws will be the same for all inertial observers. Inertial observers means observers moving with respect to each other with constant velocity, without any acceleration. That was Galilean relativity. And Einstein was forced to add another thing to that, which is constancy of the speed of light for all inertial observers. So he said that if we have these 2 axioms, that inertial frames are equivalent, and all laws of nature are true in all inertial frames. And to that we add that every inertial observer will measure the same speed of light independent of how that observer is moving or how the source of light is moving. The speed of light will be constant. He added this axiom, and out came some very surprising consequences. Things like that space can contract, time can slow down, and matter and energy are equivalent. The most famous formula in all of physics is E is equal to mc square. That is one consequence of special theory of relativity, which is simply one consequence of constancy of the speed of light for all observers. So if a moving observer, the meter stick of a moving observer will appear contracted to you, the clock of a moving observer with respect to you will appear to slow down for you, and matter and energy are equivalent, related to each other through this famous formula that energy is equal to mass times square of speed of light. That's summary of special theory of relativity. I mentioned it because it is needed to get to the general theory of relativity of 1915, which is needed for cosmology, which is what is the fountainhead, let us say, of modern cosmology, general theory of relativity. General theory of relativity came about when Einstein tried to reconcile special theory of relativity, his own special theory of relativity with theory of gravitation, with the gravitational force. And this, I mean, he struggled with this problem for 10 years. And in 1907, 2 years after 1905, he came up with what he called happiest thought of his life, which is known as equivalence principle. Basically, it says that if you are falling freely, if you are in an elevator and the elevator breaks, I mean, it gets de-anchored, it breaks down, and you fall freely in that elevator, you will not feel weight, so that acceleration is somehow simulates gravity. Gravity can be cancelled by appropriate kind of acceleration, or in other words, the freely falling observer does not feel gravity. This was the key physical insight that resulted in general theory of relativity. So I don't have to go into, I mean, these theories are not the purpose of this talk. I just want to put all the coordinates together so that we can talk about cosmology. So general theory basically says, in John Wheeler's, a later physicist, physicist at Princeton, in mid 20th century, he said it beautifully: matter tells space how to curve, and space tells matter how to move. The great achievement of general theory of relativity was that the dynamics of matter and motion was connected by Einstein with the geometry of space, or to be more accurate, geometry of space and time. So this matter and energy got connected with the geometry of space itself. Matter and energy curves the space and time around it, and in a curved space, something that falls freely will fall on a curved path. That is the essence of general relativity. You don't have to worry about the equation that is there in this slide. I just wanted to show you how does the general theory of relativity basic field equation looks like, and this is the picture that is often shown to students when we begin learning general theory of relativity as physics students, that there is some mass sitting, and if the space and time are denoted by that that matrix kind of thing, that perpendicular lines, then you can see the curvature, that where the mass is, the space-time gets curved. So now we come to cosmology. Einstein's field equations, the equations that you saw in the previous slide, they give out a universe. Einstein himself noted, the next year, he published it in 1916, 1915, he came up with the field equations. In 1917 itself, he noticed that his equations give a non-static universe. In those days, around 1915, not much was known about the universe. Our Milky Way, our galaxy, this was more or less, whole of universe. That is how it was seen at that time. Other galaxies were not known, or they were just beginning to be discovered. So universe appeared to be, the dogma at that time was that universe is static and fixed. But Einstein's equations were giving out a non-static universe, a universe that can expand or that can collapse. And Einstein thought that it's a disaster. So in order to make his universe fixed or static, he added a term. You can see this. I don't know whether you can see my cursor or not. On the left hand side of the field equation, he added a third term that has a lambda, this lambda g mu nu term. This is the only way Einstein's field equations can be modified, and this lambda is known as the cosmological constant. So he added cosmological constant by hand to make his universe static, fixed. Of course, 10 years or 12 years down the line, Edwin Hubble discovered, I think at Mount Wilson Observatory or Mount Palomar. I don't know whether Mount Palomar was there at that time or not. Maybe Mount Wilson, I don't remember. He discovered that in 1929 that the universe is expanding. He discovered galaxies, and the galaxies were running far away from each other. They were all running away from us. And the farther a galaxy was, faster it was receding from us, faster it was moving away from us. That is known as Hubble's law. So that we know now that our universe is expanding. And that is what prompted Einstein to call cosmological constant the biggest blunder of his life, because his equations were smarter than him. And his equations were telling that universe must be expanding or contracting for that matter, but it must be non-static, And he artificially ordered the universe to become static, and that is what he was predicting: expanding universe. He would have predicted what Hubble would have found, in 1929, but he missed the chance. He made the universe static, and then the experimental astronomer Hubble, he got the credit. He was the one who discovered for the first time that universe is expanding. So, and now the story, as we will see, further developed, even his biggest blunder, what he called his own biggest blunder, in a way, nature seems to respect even his blunder, because, in 1998, I already mentioned their name, Perlmutter and others. They discovered that universe started accelerating. The expansion of universe started accelerating 5 billion years ago. And that acceleration, as we will see, can be explained only by a cosmological constant. So the cosmological constant, which Einstein thought was his biggest blunder, actually there is a little bit of cosmological constant that is there in universe, which we have now found out. So that is why I say that even the biggest blunder of Einstein is respected by nature. So what kind of universes do fall out of general relativity? The Russian physicist and mathematician, Alexander Friedman, in 1922, put into Einstein's equation matter and energy, a uniformly distributed matter and energy, and he solved the equations, and he found that there are three possibilities. Three possibilities, means universe, if there is enough matter and energy density in the universe will collapse. This curve, in this graph, you are plotting on x-axis time since Big Bang, and on the y-axis the radius of the universe. So in the lowest curve, you have the universe expands, attains a maximum size, then begins to contract, and then comes to a big crunch. If there is enough matter and energy density, the universe will expand, and then it will come back on itself. Then it will have a big crunch. On the other hand, if the energy density is not enough, then it will keep on expanding, and in between there will be a critical energy density. Critical energy density, where if exactly the matter and energy density is of that critical value, then you will have flat universe, which means that universe will keep on expanding forever, and the expansion will be slowing down forever. So these are the three possibilities Friedman found by solving general relativity field equations: open universe, closed universe, and flat universe. Then before Friedman's 1922 solution, De Sitter, another physicist, had found a very interesting solution, which became interesting in later cosmology. At that time, it was a mathematical play for him. What he did was that he said that let me take away all matter and energy and just have the Einstein's cosmological constant, just have empty space. So if there is just empty space, no matter, no energy in the universe, only empty space, and that empty space has little bit of, that universe has little bit of cosmological constant, that cosmological constant behaves as if space itself, as if vacuum itself as if empty space itself has repulsive gravity. So space expands, and it expands exponentially. So in this curve, this yellow thing, if you can see, the first curve that is going straight up, that is the curve of exponential expansion. If you have only cosmological constant, or in other words, we will see later on that if we have cosmological constant as well as matter and energy, and if cosmological constant begins to dominate, then you will have accelerating expansion of the universe. This solution was found by De Sitter in 1917. Most realistic solution was found by another physicist and mathematician who was also a clergyman, who was also, you know, um, an activist of the church, you know, Lemaitre. You know, he kept both the things. He kept matter and energy as well as the cosmological constant. And he found this curve which is close to, you know, which closely describes how actually our universe is. In the beginning, after the Big Bang, when universe begins to expand, the universe is smaller. If the universe is smaller, the matter and energy density is larger. Then if the matter and energy density is dominating, then you will have decelerating expansion. The expansion will be there because of the initial push, because of the Big Bang, whatever the reason, we will come to that in a minute. Because of the initial push, the universe will expand, but the gravitational force of the matter and energy, according to Einstein's general theory of relativity, will make the expansion slow down. So that is the first part of this curve, you know, that it expands and slows down, it flattens. And then when the cosmological constant more or less becomes of the same order, or you can say that the expansion due to cosmological constant, you know, which is the repulsive gravity of empty space, that more or less compensates the attractive gravity of matter and energy. Then you have this stagnation period when universe is not expanding, but, you know, still it is expanding a little bit, and still it is growing, the size is growing. As the size of the universe is growing, the density of matter and energy is becoming less and less, and eventually the cosmological constant that begins to dominate. And you know that cosmological constant results in exponential expansion of the universe, accelerated expansion of the universe. So the last part of the curve, you know, is that, you know, this is the phase dominated by the cosmological constant. This was in 1927, Lemaitre solving Einstein's equations with both matter and cosmological constant, and comes up with this curve. You know, it was really remarkable, because this is, as we will see, this is how our universe is. So now coming to our universe, dark energy in new term, but dark energy is same as cosmological constant. Dark energy is the energy of empty space and represented by cosmological constant in Einstein's field equations. And as I mentioned, in 1998, Perlmutter, Schmidt, and Rice, they discovered, you know, that universe started accelerating. The expansion of universe started accelerating about 5 billion years ago, and that could have happened only if, the only way you can explain that 5 billion years ago, finally the cosmological constant, a small value of cosmological constant that seems to be there in our actual universe, that cosmological constant began to dominate the matter and energies attractive gravitation. So as cosmological constant's repulsive gravity of empty space began to dominate, after some 7 billion years after the Big Bang, or 8 billion years after the Big Bang, then the universe began to accelerate. This was discovered in 1998 by looking at very far away supernova, which were not accessible, you know, to earlier telescopes, but with Hubble telescopes in the Earth's orbit, you know, they could see far away supernova, and then they could conclude that 5 billion years ago, universe began accelerating, or the expansion of universe began accelerating. So that is the discovery of dark energy. Dark energy is the repulsive gravitational energy of empty space represented by cosmological constant. The expansion of universe started accelerating about 5 billion years ago. So far, if you look at the entire age of universe, which is about 13.8 billion years since the Big Bang, in the beginning, matter and energy density was higher, leading to decelerated expansion. Eventually, cosmological constant began to dominate, and that resulted in accelerated expansion. The other part, so that's the dark energy story. The other constituent of universe, the other component of universe is known as dark matter. And dark matter is something very different from ordinary matter and radiation of which we see and out of which we are ourselves, constructed, ourselves built. Earth, sun, everything including us, is from ordinary matter that we are familiar with. This dark matter is a completely different beast. It interacts with regular matter and energy only through gravitation. It does not interact with any other force. No electromagnetism, no strong and weak nuclear forces. Those forces do not affect dark matter. That is why dark matter can pass through. It may be around us and we may never discover it, or we may never feel it, because it doesn't interact with us. It interacts with us only with gravitation, and gravitation is too feeble a force we don't feel the gravitation of the air around us. And the earth has to be so massive to have enough gravitational pull on us, and we can counter that gravitational pull of earth by our hand by picking up the of pen. Pen we are picking up, and the earth is pulling down, and we win. Even we can win against the gravitational pull of earth. So gravitational force is too weak, to be felt, unless you are standing on a very massive place, massive chunk of matter called earth. This dark matter was suspected, or was in a way indicated first by Fritz Zwicky, a physicist, a Swiss physicist, in 1933. He noticed that ordinary matter is not enough to explain the observed motion of galaxies. There must be some more matter, which he called dark matter. The name was given by him, the dark matter, which must be pulling, contributing more gravitational attraction in order to make galaxies formed, or in order to make galaxies rotate or move away from each other at the observed rate. And this was then clearly established in 1960s and 70s by the observations of astronomers like Vera Rubin and Ken Ford and others too, who measured the rotational curves of galaxies. The galaxies rotate, on their axes, and when these astronomers measured the rotational speed of galaxies, they found that given the ordinary matter, given the matter that is visible in those galaxies, if the galaxies are rotating at that speed, the centrifugal force would not allow the galaxies to be formed. They will disperse. All galaxies will disperse, at that high speed. So this diagram that is at the bottom of this slide, that the top curve shows the actual rotational curve, and the dotted line shows the expected curve of galaxy rotation. But the actual galaxy rotation curve is much higher, or the rotational speeds are much faster than the maximum rotational speed of galaxy that can still keep the galaxy together. So there is a big discrepancy. You see there is a, if I can get the cursor, there is a big discrepancy. You see, and this is why dark matter is needed. So what is the story of our universe now? what are the constituent and what are the expansion like. You know, in this curve, you just notice the top curve, the red curve. In the beginning, if you follow the red curve, this is our actual universe, the red curve. If you follow the expansion, on the x-axis you have billions of years, and on the y-axis you have the relative size of the universe. If you follow the size of the universe with respect to time, you will find that in the beginning there is decelerated expansion, expanding universe, but at the speed of expansion is slowing down. And as you come to 14 billion years ago, now at this point, then you see that it is beginning to accelerate again, and in future it will accelerate faster. And this curve, from this curve you can calculate the dark energy and the density of matter. Density of matter means matter, dark matter and ordinary matter put together. So matter and energy part is 30%. 30% contributes 30% to the gravitational pull. 70% is gravitational push, which is contributed by dark energy. So in a rough way, you can say that the energy content of the entire universe is such that 70% of it is dark energy, 30% is matter, and out of that 30%, 25% is dark matter, and 5% is ordinary matter. So the matter that you see in the universe, out of which all of us are constructed, our sun and planets are constructed, all the galaxies, you know, visible galaxy are constructed, that is only 5% of the universe. 95% of the universe is, you know, dark energy and dark matter, about which we know very little. Then comes the question, then you go too close to the origin of the cosmos and you ask then, but we still haven't answered the question, why was the Big Bang? Who pushed it in to begin with? Why did it started expanding in the first place? You know? And the most, the standard model of cosmology accepted today, that explains it by something called inflationary universe. You know, inflationary universe, you know, again, a very whole semester courses are there on, you know, graduate courses are there on inflationary universe. But I will say it in just 2 lines, that inflationary universe, the idea came from many physicists, including Alan Guth, you know, who is now at MIT, you know. In the beginning itself, there was a very small droplet of what is called false vacuum. I mean, don't bother, you know, to know in detail what false vacuum is. It's a vacuum, it's empty space, but not this vacuum in which we live, you know. It's a vacuum much heavier than our vacuum, you know. And because it is vacuum and because it is heavy, it has large cosmological constant, it has large repulsive gravitational energy of empty space, because of which in the beginning it expands very fast. That droplet from wherever it came, most likely it came from random quantum fluctuation. Random quantum fluctuation gave rise to a droplet of false vacuum, which then general relativity takes over, and cosmological constant, very high value of cosmological constant in the heavy false vacuum makes it expand very fast. It becomes large, and then it decays to the ordinary vacuum, which is much lighter than the heavy false vacuum. And the energy difference between the false vacuum and the ordinary vacuum, that energy difference becomes available for creation of matter and energy. That is how the universe was created. So initial Big Bang was that exponential expansion, which was due to the heaviness or high cosmological constant of the false vacuum. It became large and then it decayed, but then a lot of energy was available to create ordinary matter and energy. That is the model of inflationary universe. And that solves many of the puzzles of ordinary Big Bang cosmology. Obviously, we don't have time to go into the details of that. But one thing that it predicts the, I mean, I forgot to mention, you know, the discovery of cosmic microwave background radiation in 1965, when 2 physicists from Princeton accidentally discovered that the whole universe is bathed in all directions with a isotropic and homogeneous radiation, which is now a microwave radiation. And the only way you can explain is that 380,000 years after the Big Bang, the universe was cool enough for the electrons to fall into protons, and for the first time hydrogen atoms were formed, and then at that time light was released, ultraviolet light was released in the whole of universe, which with the expansion of universe, that ultraviolet light, the wavelength has expanded too, because with expansion of universe, space itself expands, everything expands, so the wavelength also expands. What was ultraviolet light at the beginning of the universe is now a microwave, long wavelength, microwave background radiation. That was discovered in 1965, and then it was also discovered after the what is called the microwave mapping through satellite microscopes and so on of the entire universe, that there are anisotropies, there are some inhomogeneities in this largely homogeneous CMBR, cosmic microwave background radiation, and these anisotropies are more or less predicted by the inflationary universe, one of the grand successes of the inflationary universe model. So this is, now we come to end of the modern cosmology part. The standard model of cosmology, you can see the whole history of universe so far in this diagram, this famous diagram, NASA or WMAP diagram, that in the beginning there was quantum fluctuation. If you see at the left end of this cylinder, if this diagram, let me see if I can still get the cursor. I don't see the cursor. Here the quantum fluctuation, that droplet of false vacuum. Then you have the inflationary period, the very rapid exponential expansion of the universe. Then the blue period is when the blue part you see, that is when the microwave, today's microwave radiation was created. Then after that there is dark age, stars were not born yet, and then the first stars were born. So the light came about and the universe became visible again, and the expansion continued. Then galaxies were formed, planets were formed, long story, lot of things happened in the universe. It has been a very long and complicated story, how the heavy elements were formed and so on. We don't have time to go into the detail. Last point is that 5 billion years ago, cosmological constant began to dominate. So 5 billion years ago, the expansion began to accelerate. This is the whole of story of entire history of the universe as we know it now. Now, newest tool we have now of cosmology, of astrophysics, of gravitational wave astronomy. You know that in 2015, for the first time, the first detection of gravitational waves happened at LIGO in US, for which the leaders of the LIGO project, Weiss, Thorne, and Barish, they got the 2017 Nobel Prize. This gravitational waves has traveled at more than 1 billion years, at the speed of light. Of course, gravitational waves travel at the speed of light to reach Earth, and these gravitational waves had been created in the merger of two black holes. Since the first detection of gravitational wave in 2015, 50 more events have been detected so far. And the largest one, in the largest black hole merger, 85 solar mass black hole merged with 66 solar mass black hole, giving rise to something like 151 solar masses. The merged black hole should be 151 solar masses, but it is only something like 145 solar mass or so, because equivalent to 6 solar masses, equivalent to the mass of our 6 suns, 6 times the mass of our sun, that much of matter was converted into energy, and all that energy came out in the form of gravitational waves. Mind-boggling figures. You will have to, those of you who can do those calculations, with E equal to mc square, that formula, and you look up, Google the mass of sun and multiply by 6 and then convert that into energy. Mind-boggling amount of energy, that traveled, to reach Earth, after 1 billion years or so. So this is the newest tool of astronomy and future cosmological study. That is where we are. We still don't know much of our universe. To end the story, I will say much of our universe we don't know. We still don't know what is dark matter. We still don't know what is the physical energy of dark energy. It is just a description. We say that cosmological constant means empty space has little bit of repulsive gravitation, but those are words. Why does space have to have a little bit of repulsive gravitation? We don't know that. Then also we don't know why our universe has a bit more matter than antimatter, because if you create matter out of energy, out of the difference between false vacuum and ordinary vacuum, matter, quantum physics tells that matter and antimatter should be created in equal amount, exactly equal amount. And if matter and antimatter are in exactly equal amount, galaxies and suns and we will not be around. Matter will annihilate antimatter as they meet each other, as the universe cools down. But we do have galaxies, we do have ourselves, which means matter is excess of antimatter. And so why is this asymmetry between matter and antimatter? We don't know that. Physics doesn't know that yet. And we also don't know that initial primordial droplet of false vacuum, what force, what field, what physics is responsible for that? Where does that come from? So there are very fundamental questions to which we don't have answers yet, to which science does not have answers. And that is a very good thing, especially for young people who are going to do science, because there is a lot of things to be, a lot of very fundamental aspects of nature remain to be discovered. And many of you might be, or some of you might be future Nobel Prize winners. And if you want to win Nobel Prize in future, cosmology is a good bet. Very, very, very cosmology, astrophysics, and astronomy is a good bet. You are going to have major discoveries in coming decades, in the field of cosmology. So cosmology, to conclude, cosmology became science only a century ago, starting with Einstein's general theory. It has become hard science supported by observational data only in the last 2 or 3 decades. Most of the excitement lies in future. Cosmos now becomes the largest and the most important playground of science to delve deeper into the laws of nature. And in the end, I will just make a short comment about culture curiosity, the title that I gave to the talk. Different cultures in the ancient era were all curious about cosmos, but most of them did not make much progress towards actual knowledge about nature and universe, as this story, of modern science and modern cosmology tells. Not the Indians, not the Chinese, not the Egyptians, not the Old Testament, not even the Greeks, who were more scientific and less, religious, or less mythological. None of those. Somebody else made the main contribution, and that thing is connected with the advent of, or I would like to call, accident of modern science being born in 16th and 17th century Europe. Europe, which in the ancient times was you can call most backward or barbarian. Those parts of the planet, those parts of the civilization, by the time they arrived to 16th, 17th century, they got ahead. It's a long debate, and it's a long subject for historians of science. Why did scientific revolution took place, in Europe and in 16th and 17th century? I don't have time to get into that, but that was the reason why modern science was born, and modern science was the reason why cosmology turned into hard science. So different cultures may have had different cosmologies to start with, but they must all have now the same cosmology as hard science. Now we don't have the option, we Indians or the Chinese or whoever don't have the option of having Indian cosmology or Chinese cosmology. There is going to be only one modern cosmology, and that as a hard science will be based on rest of science. So culture in futures, or cultures will always be many, but natural science will be only one, and the same natural science will be there for all cultures to follow. Thank you.
Yeah, thank you very much. It was one of the very good lectures that we had in this series of lectures. So yeah, thank you very much. So now I think we'll take some questions. If you have. Okay, so you can either type the questions um, or unmute yourself and ask if you want. So, few minutes per question. Um, Let me make it this view. Yeah. Yeah, you know, I had a, when I was, this is one of the, as I said, one of the very nice lectures that we had. But I just wanted to ask, is it because, you know, the questions and answers in ancient, say, Indian wisdom, that though they were so abstract and answers were so abstract that you cannot formulate a real question to challenge or things like that. So whereas in European, ancient European or pre-16th century European models were so, to put it bluntly, dumb, that you can actually challenge and you can actually disprove such things. So then, you know, you are motivated to ask, to explore more. Whereas in those answers that you showed in the first slide, they were so abstract that you, unless you are very bright, you cannot approach. Oh, okay, maybe what he says is correct, I guess. So you are discouraged to ask questions.
Yes, I guess you are right. I would say the way I will say it is that, in fact, all ancient cultures asked questions which they could not answer. Because in order to answer those questions, certain preconditions had to be fulfilled. And that is what I mean, the advent of modern science. The modern science asks questions that can be answered. And when answer is found, scientifically, then that raises further questions. That kind of feedback, kind of curiosity giving rise to further curiosity, and curiosities are such that they can be actually answered. That is not so much as a difference between Indian culture and the Old Testament society or the Islamic society or the Chinese society. That is more because modern science was not available to any of the ancient civilizations. So they speculated in different ways. Some of them, as you say, I agree, some of them might be more abstract, more philosophical, more asking deeper questions. But they did not fare any better, because even though they could ask deeper questions, answering those questions was even more difficult. And the people who were asking simpler questions compared to the Indian example, even they could not answer their simpler question because they also did not yet have modern science in hand. That is why I have called the advent of modern science in Europe of 17th century as an accident. We don't understand why did it happen and why did it happen there. There are many accidents came together, many exigencies, many conditions just came together. For there was a lot of debate among the church philosophers. There was a lot of debate happened, inside the church itself. Christianity itself is split in two parts, Catholics and Protestants. Protestants were more rational and were, putting more faith in the reason, rationality of individual human being rather than on some deity. So the kind of dynamics that happened within Christianity also gave a push to the birth of modern science. And also by 16th, 17th century, the feudal Europe was changing. Capitalism was coming about, and a new class was being born, which has to displace the old ruling feudal classes. And the way they had to win over the masses was through logic, because tradition was on the side of the feudals. So the newly emergent capitalist classes, or the newly emergent bourgeois um, in, uh, uh, agency, that depended more on reason to convince people. So many things happened. Why did it happen there? We don't know. A historian probably would know, but it did happen, and modern science came about. When modern science came about, then whether the questions were simpler, like, I mean, when was universe created? Why did God say, let there be light? Simpler questions, or more philosophical questions like the Nasadiya Sukta of Indians, I mean, all those wondering questions, um, all of them could be, it took time, but it could be answered with the help of modern science. So the scientific revolution is the key answer. Whether you have to answer the more philosophical question or more direct or blunt questions, scientific revolution was the key answer. That started the process through which we could finally come to some grip over what actually the universe is about.
Okay, thank you very much. So, our students are, because they have classes, other classes they are leaving, but many of them thank you for informative lecture. And another person says that they enjoyed your talk, and
Yes.
basically,
Yes.
everybody is very grateful to the talk that you gave. And yeah, I will, this lecture is shared, and it will be on the Canvas page of our class. And also, since this lecture is really very good, and I am planning to announce in Facebook and other social media, so that for a broader audience. So anyway, thank you very much.
Thank you.
Spending the Indian evening and morning here. Thank you very much. So
Thank you. Thank you for having me. Thank you for having me.
thank you. Bye-bye.